Hey, welcome back everyone. In this exercise we are going to revisit our Fremont River model, which we built earlier. And as you may recall, that had a drain and a couple of wells, and the water flowed from left to right. And we're going to revisit that, and we're going to add a general head boundary condition in the model to simulate a pond, or a lake, excuse me. And then we're going to calculate the conductance of the sediments in the lake, and we're going to save and run that, and then we're going to apply the horizontal flow barrier package to simulate a fault. And so again, we're going to modify the model to simulate a lake using the general head boundary condition, and we're going to simulate a fault. So those two things. Alright, so let's go back to GMS. Now, by the way, it talks about, in the instructions, it says to download and unzip a start.zip file and then open the Fremont2.gpr file. I've already downloaded and unzipped that, and we're ready to open that now. So Fremont2.gpr. And here it is. Let's do a couple things. Let's frame our image to expand that. And when this model was saved, apparently the background color was set to be this darker color. I guess nowadays you'd call that dark mode. I'm going to go into the display options. I'm going to change the background color to a white background, which I think I'll prefer in this case. So what we have here, let me expand. I'm going to right click on the project and do expand all. So if we turn off the grid for a second, we have our original CAD drawing, but now we've got this lake here that we want to simulate, and then we have this fault over here. So we're going to do the lake first, and I'm going to turn on that. So that's just in the background as part of this. It's actually not part of the CAD image. It's associated with our map module, which we're going to talk about a little later in our exercises here. But we're going to use that in the background to trace out our to select the cells. So in order to mark these cells as general head boundary cells, I need to select them first. Now, in our later exercises, I'm going to show you how to define your general head boundary condition properties using points, lines, and polygons. And once you get dealing with real-world objects that have complex shapes, then selecting individual cells can be a little tiresome and not very efficient. So there is a more efficient way to do this, which we'll get to later. But for now, we're still in our stage where we're just creating a grid and editing the properties manually. And so I need to select all the cells in here. Now I could hold down my let's see, I need to be in the right module. Switch to the 3D grid module. And I could hold down my shift key or control key and select these iteratively one at a time. But if I go to the edit menu and say select with poly, select with a polygon, then I can just start tracing out the perimeter of this by clicking on each of these points around the boundary, and eventually I'll get back to right here and I double click. Oops, okay, try that again. Double click. There we go. And it's selected all of the cells inside that polygonal boundary that I just clicked with my mouse. And so now I'm going to right click and do sources and sinks. We'll say general head boundary, and we'll enter a head value of 360. Now we need to calculate a conductance. So let's go back to Excel, and I already had this little spreadsheet set up from our prior exercise, the ag drains 3, I think it was. So we're just going to change this little calculator. The hydraulic conductivity of the sediments is 0.2. Again, here are the properties. K is 0.2. The thickness of the sediments is 2 meters, and the cell size now is 40 by 40. And so let's go back here. This is area is equal to 40 by 40. The thickness is 2 feet. So now I actually need to change the units. These are meters per day now, and meters squared, and meters squared per day. So our conductance then is 160 meters squared per day. Let's go back here and do 160. Okay, now we will click outside the polygon, and let's just turn that off for a second, the background. So again, we've selected those cells and marked those as general head boundary condition cells representing a lake in this case. So the head we assigned was 360. Now if I move my cursor across here, you'll see that if you look down here in this little box, on this side the head is 342, and over here it's 355. So pretty much everywhere in the vicinity of this polygon representing the lake, the water table should be lower than the lake. So this lake we just defined should be a source of water. There would be leakage from the lake into the aquifer. And so let's save this and run. It converges very quickly because we have a reasonable value of conductance, and there we have it. So you can see, if you look at the, let me change the contour options here so we can get a better look at that. You can see definitely how the excuse me, the water draining from the lake impacts the head contours. A little bit of mounding in the groundwater occurs here, which is kind of what we would expect. And the water table under this, as I move my cursor around under this, it's pretty close to 360. So it's behaving kind of like a specified head boundary condition. It's close, but not exactly 360. And let's see how much water we're losing here. And so head-dependent boundaries, so general head would fall under these head-dependent boundary conditions. And so we have 547 cubic meters per day going in and 194 going out. So apparently, once this settles down to an equilibrium, on some parts of this you have water. This lake acts as a sink, and some parts it acts as a source. It's primarily a source, but I would guess maybe over here on the uphill side, because now if you look at the left side, you'd go just outside this boundary, and the water table is just above 360. And so over here on this side, we're probably getting some cells that are gaining water, or excuse me, where water is leaving the aquifer into the lake, but for most of it, water's going from the lake into the aquifer. And so that's kind of an interesting application of the general head boundary condition. So with that, let's look at our second step in our exercise, and that is to simulate that fault using the horizontal flow barrier package. And so we have a hydraulic characteristic of 0.00001. And remember, that is the hydraulic conductivity divided by the thickness of the fault. And it's kind of like a conductance term. And we're going to apply that right here. So the way that you apply this, again, later in our exercises, I'm going to show you how to click a line in that location and have it automatically apply the HFB conditions. But the way we do it now, or the way we do it when we're editing our input values just by selecting the grid, is we need to select the cells on opposite sides of this, one pair at a time. So we're going to start here, and I'm going to right click and select toggle HFB barrier. So when you turn that on, it marks the boundary between these two selected cells as a horizontal flow barrier. So when water goes between those cells, the flow rate is adjusted to account for that fault. And so let's put that as 0.00001. And I'm going to select that, copy that to my clipboard so that I don't have to type that every time. And I'm going to click OK. And it might be hard to see right off the bat, but if I'm going to I leave my cell edges on. I'm going to turn my contours off for a second. And it's hard to see because that cell border just turned brown. But let's modify that. Let's go into the mod flow display options, and somewhere here there is a horizontal flow barriers. There we go. And if you click on that, it pops up this window that allows you to change the display width. So I'm gonna make these. Let's make them. That's an odd set of colors. Let's make them more of a reddish color. There we go. And we'll make a thick line there. So now you can see that's marked as a clearly there's a mark there showing that that's a horizontal flow barrier. So now we're going to holding the shift key, I'm going to select that pair of cells and say toggle barrier, enter the characteristic, and we'll just keep going right down the list. Toggle barrier, hydraulic characteristic. You wouldn't want to do this for something really big and complex, but for a simple model like this, it works fine. Alright, toggle barrier, hydraulic characteristic, and a couple more, and we should have it. Toggle barrier, and we're on the last one now. Alright, so there's our horizontal flow barrier, and if you go into the HFB package dialog, it has the layer for each barrier. It has a layer, and then the I1, J1, I2, J2. So it has the row and column indices of each pairs of cells that define those barriers, and then its hydraulic characteristic here. And so that's how we set it up. And so let's save our model and run and see what happens. I should turn our contours back on. So now, if you look at the contours here, you can definitely see what's going on with this horizontal flow barrier. And again, this is meant to represent a low permeability and thin barrier to horizontal flow. And it could represent things like a slurry cutoff trench that's man-made, or typically it would represent something like a fault. Now a fault, you have this slow grinding over, thousands, millions of years potentially, some long distance of time that causes the materials in the fault to be more fine-grained than the surrounding materials, and so it tends to be a lower permeability. And so when the water flows from the left to the right side, as we see here, this barrier should act as kind of like a little dam. It's not 100% impermeable, but it should cause water to back up. And sure enough, if you look on the left side of this, I'm moving my cursor there, we have about 355.8, almost 356 on the left, and on the right it drops down to 340. 338, 340, so there's about a 15-meter drop in water table as you go from one side to the other. And if you have a fault as part of an aquifer or maybe a fractured rock system, then you will see a big change in heads, the water table elevation, as you go from one side to the other. And you could calibrate the hydraulic characteristic until you got the head differences that you observe in the field, but in any case, that's working properly as a horizontal flow barrier. And so yeah, we've simulated, we added a lake and we added this fault using the HFB and the the GHB, general head boundary package, and the horizontal flow barrier package. And so that gives us a nice introduction to these two new mod flow packages.